Morning, isn't it? Okay, so I'm Noel Gorelick. I'm one of the co-founders of Earth Engine. This is a talk on segmentation and object-based analysis. And it's a talk about a bunch of tools that I built in the past couple months, specifically so I could give this talk at this summit. It is important to note that every piece of this talk and all the tools are a massive work in progress. I was still working on those tools Sunday night or Monday night as I was preparing to give this talk the first time yesterday. So just be aware that there will be surprises. Okay? This talk is available here if you want to bring it up and see it. The talk is entirely pictures. It's been a lifelong goal of mine to give a presentation that is nothing but pictures. I almost got there. There's some words on the pictures occasionally, but this is all about concepts and results. And if you want to see how it's actually done, then this is the script that made all of the things that I'm about to show you. So you only need this one. It will get you everything else. But should you want to look while I'm talking, there is the second one as well. Okay? So here we go. This is a red, green, blue, near-infrared NAPE image, a National Agricultural Inventory Program, I think, imaging program. Red, green, blue, 1 meter image. It's a pretty typical kind of image that you might want to do segmentation and object-based analysis on. You might want to try to do object-based analysis so that you can get clean classifications. So the idea behind that is that if you classify on the mean of all the vectors inside this polygon, you'll get a nice, solid result. As opposed to classifying on the individual pixels, you might get a lot of salt and pepper noise. So a lot of people want to do object-based classification because of an improvement in signal to noise. Right? There's 1,000 pixels in here. If you can use them all, you should be able to beat your noise down by a factor of a square root of 1,000. So it's a reasonable thing to do. But that means that you need the object to be able to get to all those points before you can put them together and use them. You might also be a conservationist or someone like that, where you actually want to know the size of each one of these fields, or maybe the size of the areas that aren't fields. What's the size of the river? What's the size of the forest patch? What's the perimeter? What's the connectivity? What's the contagion? All those things that conservationists do that I don't quite understand. I just know how the math works, which is a thing. I'm not really a math guy even. So there's a lot of reasons that you might want to turn these things into objects, and they serve different purposes, and you actually end up doing different things with them. And my job as an Earth Engine engineer, and my job specifically as one of the founders for Earth Engine, is to try to make that easy for you to do. And so my goal was to stand up here and say, I have solved all your problems. Turns out that has not been the case. I have solved a few of your problems. I'm sure I've created a couple more problems along the way. But my goal long term is to say, hey, here's a simple tool you can use to do object-based analysis. You don't have to fiddle with all those things anymore, right? That's sort of the underlying Earth Engine theme, and more or less the theme of my entire career is y'all shouldn't have to fiddle with all that stuff. You should be able to jump straight to the science and do that. So I am trying to make this work. If there are things that you think will make it better, I certainly want to know about it. If you start using them, I want to know about it. And if there are tools, if there's things that you want to do, like if you really wanted to do contagion and I didn't have that, although I'm about to, then I want to know so that I can make that tool work. So that particular image is covered by the USDA crop data layer. Here it is. This tells you crop type for each of those fields, or at least what the USDA thinks is crop type. And clearly, this image is not perfect. It is highly unlikely that this field was planted with 5 different crops. It's just that their classification wasn't so good either. They might have benefited from some object-based classification in the process of doing this. But it is training data. And in fact, the class I just taught was taking an image like this and an image like this, putting them together, and doing a classification. you would sample at a bunch of points, something like this, and then you might end up with a pixel-based classification that looks like this. This is not much better than the CDL layer. In fact, it's probably a little worse. That area where they didn't know what was going on, our classification didn't come up with any better answer because we were using their data as truth to begin with. More than likely, this was planted with some crop that none of us recognized, or maybe it was bare or something like that. But what you might want to do, having done a classification like this, is one of those next steps. You might want to say, what is the area of the rice that's being grown in this region? Or blue, I think blue is rice, or we'll pretend that it's rice. So you might take this image, and you might simply sum up all of the blue pixels, or the area of all the blue pixels, and say, in this region, there were 7,000 hectares of rice being grown. But it would be an approximation. And it might be a pretty gross approximation because in a lot of places, these fields, which are almost certainly homogeneous, are not homogeneous in the classification. So you're just sort of ignoring that and saying, well, I got 7.2 million pixels. That means 7,000 hectares. And you might be comfortable reporting that number, or you might not. So what you might want to do is you might want to clean this up. And we have some tools that you would use to clean this up. You could apply a mode reducer as a reduced neighborhood, and that would let you get rid of single pixel outliers. Right? Take the mode of each neighborhood around those things. It would erase a bunch of single pixel outliers, and that would help, or that would at least give you more confidence. But this sort of thing, that's not going to fix. There's really no good way to do that on a per pixel basis that's going to get rid of those things. Same thing here in the red, right? This is sort of a bare patch in the middle of this thing. You might want that bare patch to be pulled out as a separate patch, or you might want it to go away. And then over here, that's easy on the crops. Over here, where it's a lot more ambiguous, it is clearly a lot more ambiguous. Do you believe any of these values? I don't know. But more importantly, you might simply want to say, OK, this whole patch is uncultivated. Let's cut it out. But you need the patch for that. Same thing for the river. The river's super spotty here. Not a very good classification on the river. Part of that is because these are all the more points that went into the classification. I simply sampled at each one of these little dots to get a feature vector. And in that feature vector, this is back to the cropland data layer, I said, OK, that point is that crop, whatever it is. So we've got a few thousand points. I think this was actually 7,000 points for a classifier. 10 different classes here. Not a great combination to produce a great classifier. And in fact, the result is kind of iffy. Like I said, you can clean it up. You might get to this point and say, well, the problem was I was using the red, green, blue near-infrared data directly. I classified directly on that. Maybe I can do better. So what you might think to do next is you might say, well, let's convert to NDVI. This is NDVI. You can see it doesn't help much, but I'm going to help you see that it doesn't help much. Here in the crops, the solid crops, there's still this sort of wavy pattern going on where they've done some kind of weird planting. I have no idea what's going on here, really weird planting. But these black things are what I think is rice, and they've got water in them. They're like super negative NDVI. So those are going to not come out well in the NDVI. And then over here, you've got lots of stuff just merged together. There's not really a field boundary or anything in there that helps us do anything. To point out how bad this is NDVI thresholded to 5 different levels. And you can see there's no way we could just pass an NDVI threshold over this image and get to fields. The fields are vastly different levels of NDVI. Even inside of a single field, you often have vastly different levels of NDVI. So some kind of NDVI threshold is not going to help us get to any kind of objects that we can work on. So one of our users recently went through this whole process, posted a question. I said, come to the summit, or at least I'm going to address this at the summit. The reason this doesn't work, the NDVI values are all over the place. This is 0 NDVI. There's a wide range of NDVI values in this image. We can't get to segments easily in that. A typical thing that is done in the field, especially in computer vision, is that you might, instead of working on the raw data or the transform data, you might actually work on gradients. So this is a gradient image of the NDVI. And now it's a little more promising. The stuff inside the fields is fairly low, and we might be able to threshold that away. The edges of the fields, where we're going from some kind of crop into some kind of road probably, we're expecting those to be big gradients. And so we get nice, big, bright edges here. And bright edges are good because that sort of gives us a thing that we could maybe vectorize. Those are objects, right? Those are object delineation points. The river's well delineated. The road's well delineated. Maybe this will get us somewhere. Looking at the histogram of all of this, that's nice. You know, maybe one of the points in here is a good point to threshold. Through lots of optimization and looking at a lot of images, this was the best I could do with that gradient image at a single threshold. And some of these fields, perfect, right? That's a great object for that field. This, however, is not, right? It's got a nice boundary all the way around it, and then it's got a hole. And so if I just vectorize that, the vectors are going to go right around that hole and keep going, and all of this is going to be one big object. In fact, it's going to go over here and all the way down there. Because these holes, the vectorizer doesn't know to not go through those holes. And even with all my playing, I still wasn't able to get rid of the inner field variations in some cases. They're just big enough that the gradients showed up in the gradient image. So I think we're on a bad path here, right? We've gone down several steps. We're not really going to be able to vectorize this image and just have our objects, so we need to do something else. Our first something else is maybe we just used the wrong gradient. Maybe we can't see what we need to see in there. Turns out there's a good bit of literature on spectral gradients. We had 4 bands. We turned it into 1 band, and then we tried to do a gradient on the 1 band. That was maybe not the best choice. There are a bunch of things to do spectral distance. So take any 2 spectra and compute their distance in some metric. My favorite is spectral angle, where you simply compute the angle between the vectors, the cosine of the dot product. There's also squared Euclidean distance, which is c. There's this thing called spectral information divergence, which I was not able to find anybody that has a nice picture of, so I actually don't know what it means graphically, but it's math. And it says these spectra differ by this much. And then a really cool one is Earth mover's distance, which doesn't look like the other 3. These 3 look very similar as you look at them. The Earth mover's distance looks different, and therefore there's some kind of orthogonality in it that might be useful. There's a really nice paper that says, given a bunch of spectral distances, we can compute a spectral gradient. And normally, if you're computing a gradient, you just take the min and the max of the pixels around your pixel and say, OK, my maximum nearby is 4, my minimum nearby is 2, my gradient is 2. And you might do this in the horizontal and vertical directions. And in fact, that's what this was a horizontal gradient and a vertical gradient with a sum of squares to give me just a magnitude. But that's what you're looking for is the difference, the absolute difference between all the pixels in the neighborhood. And so as you're passing some filter or some window over your image, you can take all the pixels in the window, cluster them together using spectral distance, and then you can get one that's closest to the centroid and one that's furthest from the centroid, and that distance, the difference between those two, can be used as a spectral gradient. There's some tools I made to do this. Spectral distance is the starting, spectral gradient is the end. It also turns out there's 2 things in the middle that turn into erosion and dilation for spectra. And so the erosion is, given all these pixels, which one is closest? And then dilation is, given all these pixels, which one is furthest? So the center pixel is replaced by the pixel furthest from all these things, and the erosion is the center pixel replaced by the one closest to all these things. And I haven't figured out what spectral dilation is good for yet, but spectral erosion is actually pretty good for eroding away the outliers. So if you've got a field with 1 pixel in it that's a problem, you can just apply a spectral erosion. That 1 pixel will go away, and you haven't really munged up your spectra. It was one of your spectra that went into that. So it's a little useful for cleanup, or I have used it for cleanup. But really, the whole point here is that spectral gradient is simply the difference between the spectral erosion and the spectral dilation. And since I had to compute them anyway, I turned them into functions, and you can use them if you find any use for them. or you can abuse them, which is much more likely.
Can we ask you a question?
You bet. Jump in anytime.
So the spectral distance is the starting point, and it takes all the bands in that image, or do you specify a subset of bands if you want to, or how does that work?
You would select, yes, spectral distance is a starting point for all these things. It uses all the bands that you give it, and you can always just select which bands you want to go in. But all of those metrics just say, you've given me 12 bands, I'm going to compute the 12-band spectral distance. Okay? So maybe we were just using the wrong gradient. So this image is the same image as before, computed with the spectral gradient on the red, green, blue, near-infrared bands directly, but for 3 different gradients. So this is red is they are in this order. Red, green, blue. Just stick 3 of them together to see how they look. And they look pretty much the same everywhere. That's where you get white. The blue is just where the spectral information divergence did a good job. And you can see in this image, things have gotten a little better. Most of my breaks have gone away. Maybe I could vectorize this. Maybe I could fiddle with the thresholds a little bit more to get rid of this stuff. I don't know. But it's a place you could start and simply turn these into vectors, and maybe it got you somewhere. Or maybe not. Again, going down this gradient path, there's a lot of fiddling. If you've got really obvious answers, maybe this will get you there. But also, maybe there's a better answer. So, any questions yet? Yeah.
What's the resolution of the image?
The original image is a 1-meter resolution. The stuff you're looking at, I think, is actually 18 meters. I'm using 18-meter pixels here, which means roads are basically 1 pixel in most cases. So here is what I hope. Oh, one more.
If you want to convert this into vectors, do we need to skeletonize it somehow?
You could. So there is a function for helping you do skeletonization. There's erosion and dilation, which you could do erosion and dilation on this with to do skeletonization. You could turn it into something easier, or you could actually just have it vectorize the black bits and use the white bits as the mask. Right? You mask out the white bits. What's left, you then vectorize. And as long as there's no breaks, it will kind of work. But yeah, even in the blue here, I think there are a few points where there are breaks. It's going to be iffy to go this route. People do it. It's done. Here's some tools you can do it with. Not actually what I want to talk about. I wanted to point out a bad way to go before maybe we talk about a good way to go. Okay? So I want to talk about superpixels for a minute. And this is where most of my work has been for the past month. Just like before, we're going to make a regular grid of points. And then for each one of those points, we're going to take pixels around it and collect them. And if one of those points landed in a nice field like this, then this particular algorithm that I'm using grows out, and you should be able to get the nice field. The thing about superpixels is they're not designed to be the objects. They're designed to be reduce the objects to a few pieces. I don't want to say reduce the objects to a few objects, but that's what's happening here. All right. So I'll show you what that looks like. Take each point, expand out. This is a random visualization, and sometimes it works great, and sometimes it doesn't. But the nice thing about this one is that the shapes are in there. So the river is well defined. Most of the fields are well defined, although in some cases they're split by a couple points. The roads are there. One downside of this particular approach is that all the pixels have to go somewhere. And so sometimes you will get a cluster that leaks out into a street or a road because those road pixels had to go into some cluster. And there wasn't any point on top of the road. And so the clusters just grow. And the way they grow is a little bit controllable. But they grow into ultimately collecting all the pixels. And so you end up with clusters with pixels in them that aren't so great. But we take that, we classify it, and now using the exact same tools we've already done, we classify each object. This is arguably a better or worse image, depending on your point of view. The better part of this image is that there's no salt and pepper noise, right? It can't happen because we're classifying this entire region as a single vector. So that entire region becomes one homogeneous result in the end. But it does mean that some of the roads get misclassified. The river is broken into multiple classifications because it actually includes lots of pixels that aren't in there. But the problem that we were originally trying to address of salt and pepper noise, completely gone, right? It just can't happen in this case. But it still has issues. This is the CDL for comparison, and you can see, as I go back and forth here, that's actually a better result than the CDL got, okay? This one is iffy, can't tell. This field has been broken in half, but in fact, that field is planted halfway, so it's probably a little better. Is it better? I don't know yet. I will point out at this point, and I'll probably reiterate it a couple more times, I'm an engineer. I make tools. You, the scientists, are responsible for figuring out if those tools did what you want. And often we call this loading the gun. I will happily load the gun and help you point it at your foot, but you're the one that needs to decide whether or not to pull the trigger. Okay? So the nice thing about the superpixel mechanism is that you get to pick where the pixels go. They start off on a grid, but you can say, no, don't do that. Here's where I want you to put those pixels. And you can do that to some ludicrous extremes at some point. This image I made by starting off with my grid pixels and taking my spectral gradient. Well, actually, I didn't even start off with my grid. Go back to my spectral gradient here for a second. I used this, and I used some computer vision on this to say, give me one set of pixels at the maximum distance from any white points. So that should be a pixel at the center of each good field. And then I said, OK, I've still got roads and whatnot. That'll be a problem. So invert that whole thing and give me a seed on top of the worst points otherwise, the brightest spectral gradients. Give me a seed point on top of the brightest spectral gradients. So this is the local minima. These are local maxima. I just put points at the local minima and local maxima, which is why my thing up there says the gradient min-max clusters. There were a lot more local maxima clusters, which means you get much smaller pieces. The river is super well delineated. Like every piece of the river is more or less its own cluster. Did this do a better job? I think I have a classification right there. Nope, I don't. I didn't do the classification because it, come on back. But you can classify this just like we did a second ago, and it looks more or less like the previous one. But the point is, you can put the clusters anywhere you want. So hopefully, what you would like to happen is the clusters go in at the right places, you get your results, you don't have to fiddle. That is not the case. You'll have to fiddle. I'm going to show you some tools that I've developed to help you fiddle with this and some results to help you put these in the right place. I'm basically positing that through some mechanism that I have not yet solved, we can get essentially perfect clusters. We can figure out a way to drop a point on top of all of the fields. We can figure out a way to drop a point on top of all the other things and let them grow into their own regions just fine. And then we can do things with those clusters. So I'm kind of solving two problems at once here and positing that, yeah, the first one works, even though it doesn't, and that will just get better over the next few months. Hopefully weeks, but we'll see. So a little bit more about the seeded region growing in Snick. One of our users, Genna, 2 years ago almost, posted an example of doing SLIC, Superpixel linear iterative clustering, I think is what it stands for. It uses k-means using this superpixel mechanism. I said we should really get that in. And so then 18 months later, I got around to working on it. And in the meantime, people have come up with a better answer. So there's another algorithm called Snick, superpixel non-iterative clustering. And non-iterative and Earth Engine go together really well. Iterative, not so much. Non-iterative, I was all over that. So I went and I implemented this. And it turns out it was really simple to implement. This is an algorithm really well suited for Earth Engine. And so I'm going to show it to you. So if you don't do anything else, it will just give you a grid of pixels. It will grow from the center of each of those pixels, adding in the things with the minimum distance. So it adds the closest spectrally matching pixels first, and they grow out. And there is a parameter on the algorithm that lets you define how much influence the spatial component has. So if you want a purely spectral segmentation, it will do that. If you want a purely spatial segmentation, where the spatialness is defined as the distance from the center point, it will do that, and you'll just get squares. And you can do something in between. So you can, in fact, turn that knob and see the regions change depending on how much compactness you want in them. Yep?
So previously you showed different types of spectral distances. Is this limited to Euclidean?
Right this second, Snick is limited to Euclidean distance. I'm adding that parameter any second to let you have those other ones. I finished this before I finished the spectral distances. So now that they're there, I can just bring them back in and let you do any of them. Okay? Does that make sense? Right? You change how much weighting you're giving the closeness of the pixels. And if you set it really low, then you can get clusters that go very, very far that are primarily spectrally homogeneous. And so, like this black one squishes down around into non-field fairly nicely at low numbers for spatial correlation. Make sense? One more nice thing is that there's another function called seed grid, which will let you put the seeds anywhere you want. So you can actually set them to be on a hex grid, and you end up basically with hex cells. And then you can morph those hex cells around the same way into, preserving the spectral features of the underlying data.
But you're just showing us an animation of you tweaking the knobs. This
Correct.
is not iterating to some optimization here.
There's no answer for optimized.
Right.
There's no optimized answer, so I don't know what the right answer is. Yeah, this is just it's a knob. You can play with it, set it where you think you should set it. All right. So again, as I mentioned, I'm presuming that the clustering will eventually give you good objects. But once we have clusters, what can we do with them? If you're trying to do forest conservation and you want to know connectedness and compactness and contagion and things like that, you need clusters that actually represent your forest, and I don't have that yet. We're going to assume that I do, and we're going to talk about what you can do when you've got them. So, clusters as objects. Here's some clusters. Assume for a minute that they're the right clusters. One thing we can do is, using a new tool, and this is the important part of this whole talk, by the way, reduce connected component. Previously, you could take all these things, you could turn them into vectors, and you could do all kinds of vector-based stuff. Distance, perimeter, all that sort of thing. But the process of doing that has significant limitations in Earth Engine. The size of a table that you can generate in Earth Engine has limits. If each one of these polygons has in it, I don't know, 50, 60, 100 points, though it's a pretty large feature, some of these polygons can actually, if you do this not using Snick, but wherever you got your polygons from, you can end up making 100,000 point polygons, million point polygons. And the number of million point polygons that you can fit into a table in Earth Engine before it runs out of memory is actually quite low. So we're optimized for tiles and images, and anything we can do to stay in image space means that the scale can be increased, sometimes by 4 or 5 or 6 orders of magnitude. So we want to do everything we possibly can in image space and avoid table space if at all possible, or maybe at the end you just extract your final results into vectors. So to do that, a piece has been missing, and so I built it last week. It's called Reduce Connected Components. What it does is it takes a tile. In that tile, it finds all the homogeneous pixels and then applies a reducer to everything underneath those pixels. So the cluster band is where the homogeneousness comes, and the spectral bands underneath that you can then do things with. This particular image is my original NAPE image clustered, and then in each cluster we compute the standard deviation. And the reason we do this, or the reason I did this, is because my clusters that are really good field clusters are low standard deviation, and the ones that include field and road end up with a high standard deviation. Right? This is a great example. It's got several roads in there. The standard deviation of that one is way high. So this is a great indicator of good clusters and bad clusters. It's also per band, so you're actually seeing red, green, blue standard deviation here. So the colors don't mean a lot other than the standard deviation in green was a little higher than red and blue here, but they were all low. The standard deviation in all those bands is high, right? So, and it makes a cool, pretty image. Yes?
What happens to a cluster on the edge of a tile?
There's, for all tiling operations, all tile-based operations in Earth Engine in which the tiles matter, you specify a neighborhood. So if this was my tile, you say, go this much additional and do that extra work so that you don't miss any partial objects. So that's neighborhood size. Several dozen of the functions in Earth Engine have that. And we just do the extra work. I had another point there. Oh, right. In this particular case, it might be called neighborhood size. It might also be called max object size. Because if you have an object that actually spans not one tile, but 2 or 3 tiles, if it comes all the way over to here, that's a really big neighborhood. And it's hard for us to process. You can tell us to do that. You can say max object size is 8,000 pixels. And we will try and bring all that data in and try to do that huge amount of extra work just for this one 256 by 256 tile. But you might run out of memory in the process of doing that. So to make sure that we don't ever give you the wrong answer, instead of neighborhood size here, you actually have max object size. And objects that are bigger than max object size are thrown away. They're masked out. So you'll know that we weren't able to do the computation rather than just giving you a partial computation that is going to be completely incorrect.
No, so just clarify, reduce connected components will reduce all the pixels in that cluster and then copy that output into all pixels?
Yes. So that's what's happened here. Standard deviation of all these pixels put back into all those pixels. Okay? Yeah, okay, so we go forward. So we have our standard deviation map telling us where our bad clusters are. We can threshold them straight away, saying these are the outliers. And then we can compute the spectral distance for all the pixels inside of each of those clusters. So here's one cluster. It was a problem. The spectral distance from the mean of this cluster to all the pixels in this cluster is what you're seeing here. So the field is low spectral distance because the mean is mostly field. And then we can actually find the worst outlier and stick a point on it. Okay? So this was, for this cluster, this was the worst outlier. For this cluster, this was the worst outlier. And we can use those as new seed points and grow new clusters, assuming that that was the problem point, and hopefully this problem goes away. It doesn't always, but let me rephrase that. That is not the case. But it helps, right? So here is a new set of clusters grown on those new points. Here is the new standard deviation map, much darker, which is good. Like black would be perfect. There's one cluster that's still a problem child, and you can see it's got lots of road in it, right? So we could repeat this again until we stop having clusters above a certain level of standard deviation. And suddenly, I have taken my wonderful non-iterative clustering algorithm, and I've made it iterative again. But maybe it's just 1 or 2 iterations to get there until I can make it better. Right, this is all just workaround because we don't get perfect clusters yet. But I'm showing you some workarounds so that you can use them. Okay? Okay. So, again, backing up and assuming that we've got some good clusters, we've gone through whatever mechanism it is that we need to get good clusters, we can then do more stuff with them. And this is the part I'm excited about because it's new. It's new. I'm not sure anybody's done this before. I need to go do a literature search and see if I can do this. But now we can do per cluster statistics in image space. We don't need to pull the clusters out to compute the area, for instance. Up till now, you would have had to make polygons out of all your clusters, and then you can ask each polygon for its area. But Earth Engine's got a band functor, a function that will let you produce an image where each pixel's value is its area. And you can simply sum those up underneath each cluster, and now you've got cluster area. Or cluster perimeter. And this is the one that I think is really cool. and I wore my shirt specifically to blend into this today. This one is the one that I woke up in the middle of the night and went, yes, I figured it out. So for here, what we do is we take every pixel and we take its, we find its minimum and maximum of its neighbors in the clusters. So on the edges, the minimum and maximum of the neighbors will be the other cluster, some other cluster. Whereas in the center, the minimum and the maximum of all the neighbors are the same, right? So this is cluster 12. All these pixels have neighbors with a min and a maximum of 12. These pixels over here will have a min and a max of 12 and 13. And so where they differ, I know I'm on an edge. I've got an edge pixel. So I can erase all the pixels that have the same value for min and max, and I've eroded out all the centers of all the clusters. And what's left are the perimeter pixels. And now I can compute perimeter area entirely in image space. And that's what you're seeing here. Each cluster, each perimeter is colored by its own cluster color, whatever that cluster color was. And so I don't know if you can see from the back, but there's green up here, blue down here. So each perimeter is its own. Each cluster has its own color, and we can compute perimeter area, again, by just summing what's left. All right? So the two tools being used together here are reduce neighborhood to get neighborhood pixels, what's around me, and then reduce connected component to do something with all of those inside of the cluster. Cool? Yeah, you all aren't happy about this as I am. I was really happy about this result. All right, so a couple more easy ones. This is the perimeter size, the perimeter area, just turned back into an image. Two more real easy ones. You can get cluster width and cluster height by just doing the same kind of reduction on top of a lat long image. We've got another image that gives you every pixel as its lat long. You can get the width of each cluster by just getting the min and the max of the lat and the longitude inside of each cluster. So there's the width and the height. And now you've got a lot of the base stats that are used in frag stats. So you can do perimeter to area ratio. You can do width to height ratio for compactness. My goal when I'm not talking to you guys this week is to actually just work my way through frag stats and see how many of those I can knock out entirely in image space. And then hopefully write a paper. I assume someone has done this before. I'm not so smart that I think I invented this. But we'll see. I'm going to just, how many of them are easy to do? The one I'm working on right now is contagion. So we'll see. All right.
When you say you're doing them in image space, all the pixels within a field are showing the same number. So, right? I mean,
Mm-hmm.
and so if you were wanting to do an object-based analysis, you wouldn't want 5,000 pixels with the same number.
You don't need to. You have a seed pixel. For every one of these, there is a seed pixel that is the center of the cluster. It's not the spatial center, it's not the spectral center, but it is guaranteed to always be in that cluster. The cluster can't include that. So if you want to just go get all the perimeters for some reason, you can simply sample every cluster at the seed location. And the seed band is included in everything. So you can simply, it's one call, right? You reduce region, you sample on the whole image. All the pixels that aren't seed pixels are immediately masked out because sample doesn't let you work on partially masked pixels. And then the seed pixel is sampled through whatever stats you've got. Yep.
So just backing off a little bit, when you created the clusters, you started from a regular grid, and then you added based on spectral distance. But what would happen if you started with not with a regular grid at all, but trying to go from the gradient, the spectral gradients that we showed at the beginning to find where you should put the point? I mean,
This one was not. Where was I? Well, we'll start with that one. This one was essentially that. All of the gradient minima and all of the gradient maxima. And it can get crazy. But if you don't really care, one of the reasons to do this is that my original image is actually, 10 million points. But this is only 7,000 clusters. And so if you're doing something that is limited by the number of points you can put into it, like a table or any of our table-based operations, this lets you suddenly convert. This is a crazy image, right? I would not ever advocate that these are good clusters, except this is representing 100 pixels, and they're homogeneous. Through this mechanism, there's a pretty good suggestion that they're homogeneous, and so I can represent those 100 pixels by 1 and get 100 times less data to then have to do things with. So I kind of did that. I don't think there was a seed grid on that one at all. And I thought I had one more. Yeah, that one starts at seeds. Yeah. Okay. Any other questions? Yep. No, it's fine.
Do you have any recommendation how to choose the seed size?
This gets into some kind of minimum mapping unit discussion. You want the seed size to be pretty close to the size of the things you're hoping to find. So if we're hoping to find roads, this was way too big of a seed setting. But we're really trying to find these, what is this, 40, these are 40 acres? Is that probably what these blocks are? Whatever. They're relatively big farms. So you'll note that my seeds are roughly about the size of my farms, but not because I was principled in that decision. It's like, yeah, that's a good number. Oh, there's a whole thing I got to tell you about. These algorithms and several other algorithms in the system, like connected component labeler, count connected components, there's quite a number of others. They are entirely pixel-based. So if I simply zoom one zoom level, I'm still using 32 pixel seed centers, but I'm suddenly working on twice as high of resolution data. So it is often the case that this is fine. This all works out great. You end up not zooming. Just don't zoom and you'll be fine. But then sometimes you'll want to zoom in and it's like, what's going on here? Is this on an edge? Is this not on an edge? Is that really where I want it to be? And so you'll want to zoom in on that rather than having it recompute at each new zoom level. And that's done by just forcing a reprojection. And this is the place that reproject was invented for. People abuse it all through the system. This is the place that we invented it for, so that you can say, nope, do this entire computation in this projection, and then as I zoom in on that, it will stay in that projection and I get to see it. So the important part of that, this is the big giant caveat for Earth Engine, reproject always happens last. Do all your computations, which isn't actually doing any computation, and reproject the final thing right as you're about to display it, and then we propagate that final projection backwards through all those computations. Okay, and it's super unintuitive, but that's just the way Earth Engine works. Reproject last to make all the computations happen in that projection. Okay? You won't remember that until you zoom and things get weird, and then hopefully you'll remember that.
Well, I did that last night and things got weird. Is it also applied to the inspector in the editor? Does it use a particular zoom?
Yeah, you're always using whatever's on the map unless you've specified otherwise. So when you inspect, there's actually something that tells you what zoom level it was using. It was using 76 meter pixels or something like that, and that's the answer that you're getting from that. But if you're inspecting something that's been reprojected, then it just does nearest neighbor duplication. So you can inspect at 76 meters even though you were processing at 2 meters, and it'll work out. Or other way around. Viewing at 2 meters, ran at 76 meters. You're just inspecting one of a bunch of repeated pixels. Okay?
When you're calculating the perimeters, and you know how you're doing that min-max thing?
Yep.
Are those perimeters 2 pixels next to each other, or is it
Yes.
1 pixel?
Perimeters, well, it's 1 pixel perimeter inside of each cluster right next to another one. So this one's orange, this one's purple. They're always 2 wide because there's always 2 clusters touching each other. But one wide in each one. And this is done with 8-way connectedness. So in certain circumstances, you can actually end up with 1.5 pixel wide borders because the 8-way connectedness allows that to happen. You can specify 4-way connectedness if you want that to happen, so that you can only ever have 1 pixel thick. But then you can get 2 pixels that don't actually overlap. They just touch on the corner. So it's a trade-off of 1 to 2. In reality, at this scale, neither of those matters. Any other questions? I sum the pixels that are left using the same summing technique I used here, right? This was give every pixel its own area and then sum up all the areas under the cluster. This is the same thing, but I throw away all the pixels that aren't on the edge. So I'm just summing the area of the pixels that are left.
So it's not precisely perimeter, you're summing the area of the pixels on the perimeter.
Yep. And I can divide by the square root of the area and get length. But there's a whole fractal thing that is involved here. Like, what does length really mean in pixel space? The closest I can get is, and I think, in fact, I did divide by square root specifically to get length, an approximation of length all the way through this. Yeah?
One more question. With your seeding pixels, maybe you can go back to that slide where we see the seeding pixels.
You want the wiggly ones?
One forward, sorry. No.
That one.
Yep. So with this regular grid of seeding pixels, you will have the case that 2 points fall in one object that you would have to define as one object. But here it seems that every seeding pixel initiates a new object.
Every seed pixel initiates a new object.
And is there a step that merges?
No, and that's that was the future work slide. So the big piece that's missing here, and the thing that keeps us from having more or less perfect pixels here, perfect clusters, this whole process involves growing and splitting and merging. So what I want to happen, and this suddenly becomes not Snick anymore. I need to call it something else as soon as I do this. But as these pixels grow and they start encountering pixels that don't look like what you've got, you want them to split automatically and make something else over there. That's easy. You know, you can. I'm an engineer. I want simple steps. That's the next simple step. And then once you've got them all, or more likely, as two regions end up touching each other and they say, oh, we're really the same thing, you want them to merge. And so splitting and merging is how segmentation is done. I just haven't folded it into these algorithms yet. And that's basically the next work, is trying to figure out how to not have, like, I could just give you a splitter and I could just give you a merger, but then there's a whole bunch of knobs. And you guys hate that. Remote sensing scientists hate that. So if I can boil this down to something really simple, Snick is really easy to use. It's three parameters, 4 parameters if you really want. It's super simple. That's my job, right? That's why I get paid the big bucks, is to go figure out how to boil this down to the simple parts of what you need for merging and splitting. So that's what I'm doing.
Are we also seeing the impact of the 256 pixel blocks? There's some really straight lines.
Yeah, so you're not supposed to see that. Don't look. I should go all the way back to my warning sign with the barricades. So the reason I was really excited about Snick, let's go back to here, is I can make this work without tile boundary effects by simply expanding my neighborhood and doing the calculations, et cetera, et cetera. No tile boundary effects in here at all, right? As an engineer, I think job done, no bugs, right? Turns out, not so much. Running Snick twice, and there's another step here in the middle where other things happen, somehow I'm getting tile boundaries that should not be there. Like all of this business here, right? That's a fake tile boundary. It shouldn't be there. I got a bug. Somewhere in there, some part of the tile processing is exposing a bug, and me and Mike will spend an entire day together tracking down what's probably a 1-character typo to find that tile boundary bug. But yeah, there are a couple. Any other questions?
You're using a Cartesian grid to get size metrics.
Cartesian grid to get size
So you're
metrics.
using the east, west, north, south to get
Yeah,
sizes that you
width and height, yes.
Yeah. So if you have, like, if you want to extract a road network, how would you use those metrics? You'd actually need some sort of linearity for a diagonal, for example. If you want to pull out road segments and connect them.
A thing that I think I can do is maximum length inside of the cluster. So I don't quite know how to do that yet, but I think I can figure it out. Road networks specifically are going to be pretty tricky here, because you're going to end up with very long features, and that just doesn't work in image space. So they're going to have to be broken up, and then how the breakup happens, I'm waving my hands as much as I can out here. I don't know how that's going to work.
Noel, do the clusters know who their neighbors are?
Not yet. That's what I'm doing for contagion right now. I have figured out a way to make contagion work with one example, with one caveat, and I need to add something to make that work. You can ask any pixel, you can compute for any pixel what are all of the neighbor values. So for this pixel here, I can say, tell me, enumerate all your neighbors. Go do reduced neighborhood onto array or something like that, and collect all the neighbors into something, and then I can distinct them and get them. And that's what I need to do for contagion. For all the ones in the center here, all the neighbors will be 0 or self, and so you can erase them. And so by aggregating over all of the pixels in the perimeter, where each pixel has all of its neighbors, yes, I can know all the neighbors of my cluster.
Yeah, that's good. If you know what the neighbors are, you know some statistics around them, then you can start merging. That would be a nice way to start merging
Yep.
containers with each other.
Yep. That's the general thought. During Snick growing, yeah, it's all in one place, and I have all that information at the same time. So I'll fork Snick into some kind of standard region growing thing, and then I can do that thing. And like I said, it's all about figuring out how to boil it down to the bare minimum that you need to know to say merge at this case, split at this case. And maybe that's just 2 standard deviations. If the standard deviation is below this, merge. If it's above this, split. I don't know. That seems pretty simple. If any of you have used our existing region growing algorithm, which is in test and has been in test for 5 years, it's kind of hard to use because it's got a fair number of parameters that are context dependent. So if you're working on a 5-band image, you need different numbers than if you're working on an 8-band image. And so I've learned that isn't going to work for you guys, but maybe this standard deviation option will get us there. Okay, so that's the tools. Snick, reduced connected components, some others around it. They are in 2 places. I meant to have a summary slide here, so I didn't have to do this. These are just on images, so you can do image.spectral distance just straight away. Snick and its followers and the other stuff that I'm producing around that are in a new section called segmentation. So image algorithm segmentation, and they just accumulate in there. If you are one of our users that reads the changelog on a weekly basis, you might have already seen that I released k-means and g-means segmentation options in there as well. Those are getting filled with. You should assume, change the word segmentation to test for a little while, and that's where I'm putting these things as I develop them and try to make them work. Snick is pretty robust, other than this one bug that I've got to fix about second use tile scale, or tile boundaries. So if you were to use that and publish a paper on it, you can expect that to not change dramatically. I found a issue with k-means and g-means, so if you start using those, next week they're going to change. But if you're an Earth Engine user, you already know that things change a little bit underneath you, hopefully always for the better. So we try to announce those. If you aren't reading the change logs, you might want to read the change logs to see when things change. Or I've just told you, those things in that segmentation bucket are going to change for a little bit as I try to make them better. Okay? So that's my talk. Thank you for coming. But I actually really want to know what you want to do with this. And more importantly, if there are segmentation things that you're already doing that you think work better, let me know. I want to try to make those work for everybody. If there are stats besides statistics, like the statistics ones are easy, area and width and height, those were easy, but you might not have thought of them. Again, I'm super proud of this one, mostly because I match. Things like this, like, I mean, I'm literally going to go get the fragstats package and see if I can replicate all those things in image space. And so if everything you want is in fragstats, okay, we don't have any more conversation to have. But that's probably not the case. So if there's more things that you think you want to do with object-based analysis that I have not mentioned here today, that means I'm not thinking about it yet. And I would like to think about it so that I can get you the tools you need to use. So
Have you tested this on multi-temporal features? Because it would be really nice to be able to segment something that is representative spatially for a given reference.
yeah, so I skipped that. I talked about it the first time I gave this talk. I didn't get a chance to talk about it this time. The answer is yes and no. These tools are designed to work on spectra. When you read the literature, they're expecting you to have 4 reflectance bands, and you're doing some kind of spectral distance on reflectance bands. Earth Engine doesn't care. So if you've got an image with a bunch of temporal composites in it, this will attempt to do spectral distance in time. And I'm excited about that. I think there's a whole bunch of interesting work there that is free, right? If you can build a temporal composite, and if you can't build a temporal composite, I just did that in my class right before this. So come to my next one, and I'll show you how to do that. But building a temporal composite is super easy, and then you can do all this stuff as a difference in time measure. And now, no, I haven't actually made any of these sorts of images from that, but I want to, right? That's like I said, I was literally working on this Monday night. Actually, even worse, I was back there working on this during Rebecca's talk. So, and the first time I gave this talk was 10 minutes later. So as soon as I get a chance, yeah, I want to go do this on a bunch of temporal data that I've already got built and see what I can get out of it. I think there's a lot of easy stuff that happens that way. Does that make sense? You just stack up temporal stuff, and then the per band stuff happens automatically on it.
A general question. You compute your connected components for a certain scale, and you grow, and then you obtain your objects. Have you thought on, like, if I shift, like, upscaling, I want to build a graph of them, like, in a more regional scale. So I want to see all farms of a general crop variety and industries separated, for example, like getting more, like another level of abstraction.
Oh, I thought you were asking a different question about scale dependence.
I was thinking of
I don't know how to do that.
building a hypergraph that gets on another level of semantics.
Where do you get that information from? Yeah,
Okay.
I don't have that information either, so I don't know how to do that. Almost everybody, I go out and I talk to scientists, I go to people's labs and I help them solve their problems. Every single scientist that I end up talking to is almost certainly data limited. Like, they want to do that, but they don't have that data. I don't have that data either. I don't know who has that data. So, awesome idea.
If you provide a metric of similarity among the clusters that you are injecting on a base level, if I somehow say these objects, they have higher similarity than others, so I'll be reaching splitting on another.
Are you talking about not spatially now? It's just here's a bunch of farms, find the ones that are more similar than others?
Yeah, but
That's a straight up cluster. I mean,
other objects that connects them.
you can, so
The Gaussian graph.
all you need to do, you don't even need to do that. All you need to do is here, where you've got per pixel things or per cluster things, you can now apply all our other tools on the seed points. So you could simply just k-means cluster the clusters, right? So that's part of the point of Earth Engine, is get everything sort of into a standard shape so that all the tools will work on whatever's there. K-means clustering these results, trivial. Classifying and clustering these results, I showed you classifying. That's the whole point, is to let you do those now not on single pixels, but on whole clusters at once.
Basically, I would be applying those classifiers not on the image anymore, but actually on the object, so the process
you can still stay in image space. So all those things work in image space as well. You're just masking off every point that's not under a seed. And so instead of working on 100 billion points, you mask out all the ones that you don't want, and you're left with 100,000 points or 50,000 points. And it works the same way. Anybody else? Anybody using object-based analysis and going, man, this is not the right thing I need? No? All right.
Do you have some example scripts that we can?
Yeah, everything you've seen is in one script, which is in that repository, which is that link. So if you've got the presentation, you've got that link. If you take a picture of that, you've got that link. If you send me an email and say, where was that? I will send you a link to my repository.
Is there an easy way for, obviously you can sample the seeds to make it into a feature collection and whatever. If I want a feature collection to have each feature in this feature collection to have a short list of all the neighboring clusters, is there an easy way of doing it?
As I mentioned, easy is not, nothing is easy yet, but here, as I was pointing out, it's 1 or 2 lines to get all the clusters per pixel, but then you can just aggregate them together over the cluster. Yep. So I will stick that example in there. Contagion, I have to do this for contagion. That's the next one I'm working on. So at the bottom of the script, in a day or 2, you'll see a section on how to compute contagion. And that is get me all my neighbors and then the frequency of all my neighbors. So it'll work. Or I will make it work.
Is this going to work only for cluster computed in Google Earth Engine, or can we import a raster with already the cluster defined?
Interesting. Will this work on things that didn't go through Snick, basically? This will work just fine. Reduced connected component. Where is it? There we go. Reduced connected components just wants a map of clusters. It doesn't care where that came from. So here, if I'd uploaded this image, I wouldn't have the seed points. That's fine. It's just using everything in that homogeneous region. So yeah, you don't have to get the clusters from us. You can get them from somewhere else. You could, in fact, use the crop data layer directly to do connected component with this. Yeah, it would work. Yes?
A plug for a hackathon. So Jeff is playing with a bunch of knobs for this sort of thing, right?
Yeah.
I'm not quite sure what else he's doing, but there's a whole hackathon session on this.
Right. Jeff Cardo from McGill University has a hackathon on segmentation. He has a meta goal, so he wants to help you build a good segmentation for whatever it is you're looking for. But he has a meta goal of trying to collect what are good segmentation parameters for different use cases. So if you're in forestry, you might want to find you might have a completely different set of clustering and segmentation parameters than if you're doing water quality or something like that. So he thinks that there's there would be some interesting things to learn in comparing the across application results. I think he's silly, but we'll see. It'll be fun.
Can you just say, you said that the last spectral distance is very different, the Earth movers. In what way is it different? Do you have any?
I don't have a quantitative, so I haven't seen a good description of what Earth movers distance does as a picture, but I can show it to you and simply point out how it looks different. examples, segmentation, run. And I think Earth mover's distance is still in here. Yeah, right there. Yes, EMD. So this thing's running away. We will zoom in. Doot, doot, doot. That's the same picture you've been seeing over and over. And we'll turn off all these and load up the gradients and the Earth mover's distance. So there's the gradients with slightly different stretch than you saw, but you should be able to relate to what you just saw. And then there's the Earth mover's distance. And among other things, it's quite bright. It's much brighter, but it really works out differently. So I mean, we can fiddle with these stretches here. So that kind of brings it to the same normalization. And one of the things that's quite different is that these inner cluster things stand out a lot more. But all I can do is wave hands here. The connectedness is good, right? The connectedness is actually a little better than before in some cases. I don't know. It just looks different. If I throw that one in with any of the two others as a 3-color composite, it always stands out regardless of how the stretch works out. So it's just a different kind of measure. So no. I'll go with no, I can't answer that question, which I hate. All right, anybody else? Sure. Even big. Oh, hello. Apparently I'm out of time.
Random question. How much of it is part of your dissertation?
My advisor's sitting here in the first row, so directly none of it. So my dissertation's not technique-based, or not about my techniques. Indirectly, maybe a lot of it. That's a long conversation, but my dissertation is about your techniques and how they're all the same. That's the entire elevator pitch, right? That's as far as I've gotten. That is the one sentence on my research proposal. Part of my job is trying to make it easy for you guys to do this stuff. If I can boil this down into 3 lines and you've suddenly got clusters with all the frag stats, you can go worry about conservation and not have to worry about how to do the computation. That's my job. But it's also interesting as a research topic for, okay, the things you want as a forest conservationist actually are quite similar to the things you want as a water quality manager, which are very similar to the things that you want as a poverty mapper. And that's what my dissertation's all about. Wow, I actually said that in front of a crowd of 100. That's, yeah, I guess I'm committed now, huh? Anybody else? What am I missing? What do you need that I didn't do? If you wanted to just if you wanted to beat down the signal to noise, beat up the signal to noise, beat down the noise on a simple cluster, this step here, where you've done find a bunch of clusters, replace the bad ones, and go from here, I think that's a quite reasonable technique to just use. Every one of these clusters, you can now beat down the noise by a factor of, in this case, 100. Because there's 1,000, 10,000 points in some of those clusters. Maybe not 10,000, but you can average together a whole bunch of points for a much higher signal noise if that was the limiting factor that you had. If you're working with an instrument where your signal to noise is the limiting factor, I'm interested, because that tends to not often be the case. unless you're looking for maybe trying to distinguish between two species of similar trees in the Brazilian Amazon, then signal to noise, or a piece of the signal to noise is interesting. But yeah, and so since you asked about my dissertation, I'm always interested in what you're doing. One, so I can help you do it, but two, so I know about the breadth of what people are trying to do. So yeah, like I said, if you've got a signal to noise limited classification problem, I'm super interested in at least knowing what that is, and then maybe I can help you solve it.
This is exactly, I think, what this hackathon, well, not the hackathon, but the future idea is if you think about MSS and you try to find transitions or changes in the MSS data, it's not good enough. So if we have clusters with Snick.
If you're looking for clear cutting, it's fine, right? But if you're looking for long-term degradation, yeah, you're right. It's much lower signal noise than you want. So, but yeah, that's interesting to me. Okay, so a feature of this talk being new is that it's short, which means you get an extra 20 minutes in the coffee line before anybody else gets to the coffee line. So we'll call that a bonus. But yeah, thanks for coming. And please let me know if you're able to use these. I'm very interested in that. If you're able to use these for a specific application, I'm even more interested in that. And where they don't work for you, I'm really interested in that because my job is making them work for you. So let me know where it's not working. Thanks for coming.